Howdy class, I see you're present, which is good. I know you're probably sleep deprived right now, but forget about that, your exams are coming, and according to the law of exam, sleep deprivation is never a problem. And I survived all that stuff in my high school year, so if I can do it, so can you. Anyways, we have reached the last chapter of physics, so let's make it quick. You guys like the font I use? I chose the two things you guys like the most, comic and sense. So light and colors. Now, what is light? Light is light. Nothing more. Just kidding, it's an actual explanation. So the first theory came from the Greeks. They thought our eyes work like flashlight, as if our eyes can produce its own light. They probably theorized it when they saw a cat. In the 300 BC, Euclid worked out that light mostly travels at a straight line and deciphered its geometry, like how it bends and stuff. In the 10th century, Ibn al-Haytham debunked Greek's theory by setting up a tent with a hole and two lanterns, which proved that light exists outside our body and that our eyes are just simply receivers. Here's a recreation of what probably went down. As you can see, there's a tent and two lanterns outside. And inside the tent you can see two spotlights produced by the lantern. When one of the lantern is covered or just gone, there's only one. Same goes with the other lanterns. Anyways, in the 1676, Ole Romer noticed something in correlation with eclipses and orbits, which I still do not understand, and worked out that light traveled at a speed. Isaac Newton used a prism to separate colors and proved that colors is an intrinsic property of light, and eventually figured out that white light contained every colors. With this and the double slit theory, he theorized that light is a wave. But despite the evidence though, Newton and many others held on to the corpuscular theory, which theorized that light is particles. That makes the part 1 of history of light theories. In 1800, William Herschel, like Newton, used a prism to break light into colors and measured the temperature. When he reached past the red, he noticed that the temperature increased. This led him to believe that there is an invisible light, as he called it, heat rays. It is known as infrared today. Johann Ritter, after the heat ray theory, he decided to test the other end of the spectrum, which is just past the purple, and found that chemical reaction happens the faster there. He called it oxidizing ray, but today it is known as ultraviolet. In the 1876,
Do you ever wanted to pronounce this correctly? Well, I know some of you struggle.
In the 1876,
So, in our website, we teach you just how. Go to worldwideweb.iwillscammyouforlife.com.
1867, James Clerk Maxwell unified electricity and magnetism, then calculated that the speed of electromagnetic wave was the same as light, which is whatever that number is. This killed the particle theory at the time. Emphasis on at the time. And that makes the part 2 of history of light theories. In the 1918, Max Planck developed a theory about how light spread across the spectrum in little bits he called quanta, though for this theory to be true, light had to be particles. Albert Einstein then realized that Mach's theory could explain the photoelectric effects. If light is a packet of wave, or also known as photons, it could explain why shining light beam on a metal releases electron. For those of you who want to know, photoelectric effect is a phenomenon in which electrically charged particles are released from or within a material when it absorbs electromagnetic radiation. And that makes the part 3 of history of light theories. Now, is light a wave or a particle? Naturally, the answer is yes. Now the properties and nature of light. Light is a form of energy which is radiated from a source and is detected by the eye. Light is a member of the electromagnetic spectrum which is visible to our eyes. It is also a form of energy which is a heat carrier. EM waves do not require a medium for propagation. Electromagnetic spectrum. From decreasing energy, it is gamma ray, X-ray, UV ray, visible light, infrared, microwave, and radio wave. That is the drawing present the wave. As you can see, gamma ray has the highest frequency and radio wave has the longest lambda. And then this is just a simple diagram of the parts of wave. Now the characteristic of light. Reflection is the ability for light to reflect or bounce off of surfaces. Refraction is the bending of light as it passes through from one transparent surface onto another. Diffraction is the ability for light to pass through slits or barrier. Interference happens when two waves overlap each other. Reflection of light. Normal reflection happens on a smooth surface, and it also has light rays that are parallel to another. Diffuse reflection occurs on a rough surface. The light rays are in random directions. Here's a rendered example of normal reflection and diffuse reflection. Refraction of light. As you can notice here, the pencil here looks broken. As for the reason why, is because the pencil is already broken. Now for the real reason, refraction is caused due to the change of speed in light when it enters from one medium to another. Here's a diagram of it. When light passes from optically rare medium to an optically denser medium, the speed decreases and the ray moves closer to the normal. Same goes for the vice versa. Air is an optically rare medium, while glass and water are optically denser medium. As for why they are named like that, I do not understand. The law of reflection. Why is this light not before the refraction light? I do not understand. The incident ray, reflected ray, the normal lie on the same plane. The angle of incident is equal to the angle of reflection. Incident ray refers to the source light, while reflected ray refers to the light that are reflected off of it. Normal refers to the line defining the incidence ray and the reflection ray. Every surface obeys this law. Here's a diagram of it. Now here's an example question which I forgot to put an animation and I forgot to use that special font. Given two adjacent plane mirrors, mirror AB and mirror BC, which forms an angle of 120 degrees as shown in the figure below, if a beam of light strikes the mirror AB at an angle of 20 degrees from the mirror, complete the figure to show the path of the ray after it hits the surface of mirror AB. B. Find the angle of incidence at AB. C. Find the angle of reflection at angle BC. I'll give you 20 seconds to answer this question because I'm a nice guy. Time's up. I see you guys haven't answered it. Shame on you. So for A, this is how the diagram look like. And for B, the angle of incidence. If you guys know basic math, you know this, how angles work. The angle of incidence is equal to the 90 degrees minus 20, which equals to 70 degrees. For C, x equals 180 minus 120 minus 20, which is equal to 40. And then here equals the angle of incidence equals 90 minus 40 equals to 50 degrees. Dispersions of color. Dispersion refers to the separation of white light into different colors of a spectrum due to its refraction as light passes from one medium to another. Here's a drawing of it. Color wavelengths. Infrared is 730 nanometers, red is 700 nanometers, green is 500 nanometers, violet is 400 nanometers, ultraviolet is 270 nanometers. And where's the rest, you may ask? Well, I don't care about it. The three primary colors of light are red, blue, and green, basically RGB. Additions and subtraction of colors. Red plus blue equals magenta, green plus blue equals cyan, and green plus red equals to yellow. And red plus green plus blue equals to white. Red plus orange plus yellow plus green plus blue plus indigo plus violet equals to white. This shows us that even if we are all different colors and races, in the end, if we are all together, we are white. Subtraction of colors refers to the removal of color frequency as white light passes through a filter. This is a diagram of color addition, and this is a drawing of color subtraction. Now, to calculate the frequency wavelength and the energy carried by light, here is some formula for it. The speed equals force frequency times lambda, or wavelength, which in this case, since we're talking about light, we'll use the speed of light, which is 3 times 10 to the power of 8 meter per second. So the speed of light equals to frequency multiplied by the wavelength. Energy is equals to h multiplied by frequency. H here refers to the Planck's constant, which is equals to 6.63 times 10 to the raised to the power of negative 34 joule second. Now here's a question. Determine the frequency and energy carried by the red color. I'll give you 30 seconds seeing how you've proven yourself to be incapable of answering such simple questions just now. Time's up. I see no one has answered it yet again. Is my teaching method wrong or something? So to answer this, the wavelength is equals to 700 nanometers because it is red. 700 nanometers is equal to 700 multiplied by 10 to the raised to the power of negative 9 meters, which equals to 7 times 10 raised to the power of negative 7 meters. Frequency is equals to the speed of light divided by wavelength, and calculate that. 4 times 10 raised to the power of 14 Hertz, and then the energy is equals to Planck's constant multiplied by frequency, and calculate that, and you get 2.65 times 10 multiplied by negative 19 joule. And that's all, folks. Anyways, that's the end of it. I hope you all understand. If there's anything you question, please don't hesitate to ask, because I cannot help you if you do not bother to help yourself. And where is everybody? Why is there only one of you here? You know what?
I have the knowledge, not the authority.
So, good luck failing the exam. See you guys in the next semester, I guess. This teacher sucks. I'm gonna start folk poetry.